Okay, so today we have another session of our seminar, and we are happy to have Willi Kepplinger from University of Vienna. And Willi will tell us about interactions between contact topology, Riemannian geometry, and spectral theory. The floor is yours, please.
Thank you very much, Roman. I'm happy to have an audience today when talking about my stuff. So when announcing this talk, I might have been overzealous. Let's see whether we actually get to spectral theory. But I'm gonna try to give a brief intro to contact topology. Then I'm gonna talk a little bit about how and why you would want Riemannian geometry and contact topology to interact in some way. You know, why it might be even natural to try and make this work. And then I'm going to provide some sort of outlook, which is mostly an invitation for people to keep this interaction in the back of their mind, because there's a couple of sort of interesting, let's say, subdisciplines in geometry, topology, and also, surprisingly, for example, fluid dynamics that are interacting exactly at this point. So yeah, that's the structure of my talk. So let me start by giving you some sort of approximation of some approximate knowledge of contact topology. So this is my brief intro to contact topology. And so let me start by introducing the basic objects that we have in contact topology. So 1.1 basic objects. And so naturally we start with a definition. So let me remark that all I'm gonna talk about today is in dimension 3. There's natural generalizations of what I'm talking about to higher dimensions, but well, it's just simpler to stick to dimension 3, and actually more things work in dimension 3 because contact topology is much better developed in dimension 3 than in high dimensions. And so all my manifolds are going to be three-dimensional. And furthermore, they're going to be oriented. So somehow there's a preferred equivalence class of top-dimensional form that we have chosen on this manifold. Yeah, let me know if any of these somehow prerequisites are not familiar to you, then I can expand on this. So the first definition is a positive contact form alpha on, well, M. So again, that's a three-dimensional oriented manifold, is a one form satisfying alpha wedge d alpha greater than 0. So what I mean by this is alpha wedge d alpha is a three form on an oriented three manifold. So that means at every point it defines a determinant. And well, that's not quite true. It defines a multiple of a determinant, and I want this multiple to not only be 0 anywhere, I also want it to be greater than 0 relative to the volume form that was chosen for the orientation of our manifold. And here, I don't know if you have any intuition for what exactly alpha wedge alpha.
Do you write or you don't see anything more? Participant asked a question in the chat. Did you see?
No, I did not see that.
Maybe that he only wrote to me. Yes, he only wrote to me that he didn't see what you write. So I think that you write everything that's okay. That's just.
But basically, so there is a question whether you could write bigger letters. So that's all.
Aha. Yeah. Okay, yeah, for sure. I can write larger. No problem. And so I don't know if you have any intuition for what the kernel of a one form looks like. I'm going to comment on this in a second. So let me first get to the second definition. A co-orientable contact structure psi well, is the kernel of a contact form. Indeed, let me put positive everywhere. So positive contact form, let's say positively co-oriented contact structure psi. Okay, what does any of this mean? So you might be familiar with Frobenius theorem, Frobenius integrability theorem. This tells you that if you have, if we specialize to a three-dimensional manifold, then Frobenius tells us, Frobenius theorem tells us that given a nowhere vanishing one form alpha, such that alpha wedge d alpha is identically 0, the kernel of alpha, so this implies, so if you have given such a one form, then this implies that the kernel of alpha defines a foliation. So let me give you an example. If we're in R3 and we look at dz, where z is just one of the coordinates, then the plane field is just, you get at every point a plane that is just horizontal. And clearly the xy planes with fixed z coordinate have the property that the tangent spaces are exactly the plane field defined by dz. So by the kernel of dz. Okay, so this is Frobenius theorem, and basically this condition alpha wedge d alpha greater 0 tells you that at no point in your manifold does the one form alpha define a plane field that comes from the collection of tangent spaces of submanifolds of M. Okay, so here's two pictures which are supposed to
excuse me, I'm sorry, can I say something? Are you writing something?
In general, yes.
Yes, but then I believe none of them are seeing what you're writing now.
Well, I don't know. I can see what's written. I don't know. Maybe it's your problem. But...
I mean, because how come like presenting math work without writing?
No, there is a writing. I don't know. Like I can see what appears on slides.
Yeah. Okay.
Can anybody, like, what about others? Like any issues for others? Because personally, I can see what appears.
I can see all of them.
Okay. So it looks like maybe it's a problem on your side. Maybe try to restart the Zoom. Like, I don't know, get to the session and then you'll be able to see what's going on. Yeah, please continue with this. Sorry.
Okay. So with this in mind, let me give you two examples of such plane fields. So I'm going to go to a new page now. Okay, so what you can hopefully see here is a plane field in R3, and it's defined by the one form dz minus y dx. And it looks exactly like this. And it has this particular property that that alpha, which is now dz minus y dx satisfies alpha wedge d alpha greater 0. So why is this? I don't know how familiar you are with exterior differential calculus, but the essential thing is that the exterior derivative, it kills all exact forms. So dz and dx are going to vanish, and so what you get here is that d alpha is just dx wedge dy, and alpha wedge d alpha, you can briefly calculate, is dx wedge dy wedge dz, which indeed is greater than 0 when measured with respect to the standard volume form that you have on R3, which is of course exactly dx wedge dy wedge dz. So it satisfies this property, and indeed you can convince yourself that this collection of plane fields precisely does not come from the tangent spaces of embedded submanifolds. Okay, and this is an object that people have been interested in for some time because it appears quite naturally in many contexts, most notably Hamiltonian mechanics. There's other examples of such context structures. Let me give you one more example, which is also in R3, but which is translation invariant in 3 directions, and so you can define it also at least in a compact object, because ultimately we're going to talk about compact objects. So this example could be defined on the 3 torus, and alpha is given by sine z dx minus cosine of z dy. And again, you're going to see that alpha wedge d alpha is nowhere vanishing, and if I did the signs correctly, it's even greater than 0. And yes, so these are 2 examples, but we're not quite done yet with introducing basic objects. There's one more thing which I have to introduce. So let me define this here. So given a contact form alpha, yeah, let's say positive again, just so I'm consistent throughout. There exists a unique vector field called R sub alpha, the Riemann vector field, the Riemann vector field associated to alpha, satisfying 2 properties. The first one is that d alpha with R alpha in the first slot is just identically 0 as a 1 form. And secondly, we want some normalization condition, which is just that alpha applied to R alpha is identically 1. Okay, so this is, of course, not just a definition, but in reality also a small lemma, but it's a pretty basic lemma. The point is that the contact condition alpha wedge d alpha greater 0 is equivalent to saying that d alpha is non-degenerate as a 2 form when restricted to the kernel of alpha. This means it has a 1-dimensional kernel, and so it defines a vector field up to normalization, and the second condition then gives you the normalization. And so you can somehow naturally associate this vector field to a contact form. And now, interestingly enough, this vector field contains a lot of topological information of this plane field. And if I have enough time, I might come back to that. Let's see how things go. Perhaps I can give you an example of the Riemann vector field for one of the contact forms I had above. So for the contact form that is given by dz minus y dx on R3, R alpha is just the dz vector field. And for the second contact form I had, so for T3 with this contact form alpha equal to sine z dx minus cosine z dy, R alpha is sine z dx minus cosine z dy. Okay, so, and indeed, it's somehow a quick exercise to prove that for whatever context form you have, you can associate this vector field. Okay. Now, since we've introduced this new structure on a three-dimensional manifold, it would be nice to talk about equivalence of structures, right? So we have, you know, for a Riemannian metric, the most fundamental notion of equivalence is that of an isometry. And I'd like to introduce something analogous for a context structure. So let me define this now. So definition. Two co-oriented contact manifolds, meaning, you know, you have a contact three manifold, in this case 2, M and M prime. You have two co-oriented contact structures. They are regarded as equivalent and we say they are contactomorphic if there exists a diffeomorphism psi from M to M prime such that the pullback of alpha prime is some multiple of alpha, where f is, since we're in the smooth topology, a smooth function on M that is nowhere vanishing. Let's say it's positive. This condition, you know, if you've never seen this before, looks a bit strange. You know, usually when you define such notion of equivalences for geometric structures and manifolds, what you require is that the pullback of one structure is exactly the other structure. But remember that we're not really interested in the contact forms alpha, but really just in their kernels. And let me perhaps say that this condition really is equivalent to saying that the push forward of psi, so of our diffeomorphism, applied to the kernel of alpha is exactly the kernel of alpha prime. So what's being preserved here is not necessarily the one form that defines the plane field, but the plane field itself. So that's the fundamental notion of equivalence for contact manifolds. And this sort of brings us to our first structure theorem for context structures. So that's the Darboux theorem. Darboux theorem. So let M alpha be a three-dimensional contact manifold then for all points in the manifold, there exists a neighborhood of that manifold, of that point, such that you know, the contact manifold UP with alpha restricted to UP is contactomorphic to a neighborhood of 0 in the contact manifold R3, dz plus 1/2 r squared d theta. Let me give you a picture here real quick. Okay. So what the Debye theorem is saying is that locally, every contact manifold, in this particular case, as that dimension is 3, but doesn't actually matter. Locally, every contact manifold looks like the picture that you can see right now. It's exactly modeled on a plane field, which you can just write down. And it's exactly the kernel of this form that you can see here. So dz plus 1/2 r squared d theta. And you can see this characteristic rotation of plane fields that precludes the possibility of the plane field coming from a foliation. Okay, so that's a very interesting theorem. In particular, it tells you that contact topology is very different from, say, Riemannian geometry, where it's absolutely not true that you have a local model for your geometric structure near any given point. Indeed, for a generic Riemannian metric, it's even true that no 2 points have neighborhoods that are isometric to one another. Yeah, this is not the case in contact topology. You have these local models, and so it's a much more flexible theory than Riemannian or, for example, Lorentzian geometry. And so this is somehow the first indication that maybe, if you try to marry Riemannian geometry and contact topology, maybe there's some sort of trouble. However, from the view of contact topology, what it means is that in order to study these objects, don't look at them locally, but instead try to understand their global properties, because locally we understand perfectly well what's going on, that the Debye theorem just tells us. So instead, let's try to understand their global properties. And so I'm just going to say a little bit about global properties of context structures. So in many ways, the study of contact topology, it's an extremely, contact topology is an extremely flexible theory. And I think the best instance for seeing this is the so-called gray stability theorem. So we have a theorem, gray stability theorem. And what it says is the following: let alpha t be a, okay, let's say smooth, it's not really necessary, but let's say smooth, one parameter family on a compact. Now this is important, on a compact 3-manifold M. Then there exists a 1-parameter family of diffeomorphisms. So this I'm going to call psi sub t, such that the pullback along psi t of alpha t is some smooth 1-parameter family of functions ft times alpha 0. So here somehow the parameter range that I'm imagining is t in the closed interval 0, 1. In particular, what this means is that if you take a context structure and you deform it a little bit, you just add epsilon times some one form, then you are not going to change the contactomorphism type of your contact manifold. And something, you know, and on a more global level, if you can find a one-parameter family of contact forms that connects your initial contact form alpha 0, so let's imagine here that we have a curve in the space of contact forms, and it connects alpha 0 to some contact form alpha 1, then, and you know, along this path, you always satisfy the condition that alpha t wedge d alpha t is greater 0, then it's already true that alpha 0 is, you know, m alpha 0 is contactomorphic to m alpha 1. This is, you know, an incredible flexibility result. It's not actually that hard to prove. It uses a fair bit of exterior differential calculus, but ultimately it's you know, one of the very early results in contact topology. The cool thing about this is that it shows you just how different contact topology is from the more rigid geometric theories. So let me give you a concrete example for this. And push this away for now. Here. So let me give you somehow some very contrasting, very starkly contrasting picture here. The space of Riemannian metrics. Riemannian metrics is convex. So i.e., if you have two Riemannian metrics, so G0, G1 Riemannian metrics, then any convex combination of G0 and G1 is also a Riemannian metric. Okay, what does this mean? Well, this means that the space of Riemannian metrics, so let me give this a name. I'm going to call this Kali G. G is convex. In particular, it's path connected. So this means that, you know, fix any manifold, let's say S3, and you give S3 some Riemannian metric, and then you pick another Riemannian metric, and now you interpolate between them in such a way that for every t, you still have a Riemannian metric. Let's say there's linear interpolation here. Then the curvature properties of the metrics in between, they radically change. You know, in the contact case, if you look at this one parameter family, you would get equivalent objects, you would get equivalent contact structures. But in the Riemannian case, basically you can, you know, using one parameter families, you can do whatever you want to your Riemannian manifold. And certainly you're not going to end up with equivalent objects as Riemannian manifolds. And so having a, you know, this one parameter family preserves the structure that you're looking at is a very special thing and indicates very high flexibility of your theory. On a more maybe technically difficult level, there's this so-called, there's a fundamental dichotomy in contact topology. Fundamental dichotomy. You know, as I was already indicating, in contact topology, you are not looking at local invariants of your geometric structure or topological structure, but instead at global ones. Now there's let's say we have some manifold M again. And it turns out there's a very nice somehow pair of properties that are mutually exclusive, which very roughly classify your the set of context structures. So here we have the set of context structures, and each context structure falls into one of two categories. Either it's over twisted or it's tight. And what does it mean to be over twisted? It means that your let me make this a bit bigger. It means that your contact manifold contains a copy of the following space. So a contact manifold alpha is called over twisted if there exists a copy of R3 cosine R dz plus R sine R d theta. So of this contact manifold inside it. In other words, if your contact manifold contains a subset which is contactomorphic to the open contact manifold that I've just written down, your contact manifold is called over twisted. The reason, okay, and every manifold that does not have this property, so if alpha is not over twisted, I'm going to abbreviate this with OT, then it's called tight. All right. The significance of this dichotomy is that basically for all those context structures that are over twisted, there's a very strong classification result due to Eliashberg in, I believe, the late 80s, in which he shows that understanding extremely general properties of over twisted context structures ultimately just comes down to algebraic topological properties of the associated plane field. So there is somehow nothing deeper about over twisted context structures than the algebraic topology. That is not quite true. So that's the way people often somehow present this result of Eliashberg. There's something slightly subtle about it, but I'm not gonna somehow talk about this to a general audience. I believe that probably does not make so much sense. But basically, what to keep in mind is that there is like a large class of context structures on closed three manifolds that are reasonably well understood. And then there's those that are absolutely not understood yet. And these are called tight context structures. Okay. Please let me know if you have any questions about this. Of course, I'm just sort of dumping a lot of background information on you. Let me know if there's something I can expand upon, if there's something where you feel like you're lost and I can just help you get back into the talk with a quick comment or pointer. If not, I'm going to move on to the Riemannian geometric part of things. So, to Riemannian geometry. Yeah, basically, why and how. So why does this come into the game here? Well, let me start with a couple of very general remarks here. So basically, the thing that makes context structures interesting is the fact that they are twisting. They're exactly not plane fields induced by a foliation. So you would like to understand their twisting and the extent to which they twist. Well, maybe it's a good idea to quantify the amount that they twist by them, right? So that's somehow the very fundamental idea that people already had back in the late 80s, early 90s. Yeah, I think it was still a very naive idea in the sense that no one really proved anything about it, but people thought that maybe using some quantitative measure of twisting is a good idea to understand the topology of plane fields. So that's somehow the first point. So try to quantify twisting of plane fields. And of course, the most natural way of doing that would be using a Riemannian metric. You need an angle or a measure of an angle at every point. Well, okay, so that's almost already a Riemannian structure, a Riemannian metric. Now, the other point is that philosophically, Riemannian geometry is extremely powerful in low-dimensional topology. So let me put it like this. Riemannian geometry dominates in low dimensions. What I mean by this is that classifications of low-dimensional closed manifolds rely on Riemannian geometry, or at least Riemannian geometry provides an extremely powerful framework to classify low-dimensional manifolds. So remember, for example, that if you want to classify surfaces, so now this is dimension 2, then you want to classify closed two-dimensional manifolds. Let's say they're orientable, then the only things you have are S2, the 2 torus, torus with genus 2, and then torus with surface of genus K and so on. But all of these can be realized as quotients of model spaces. So all of these are quotients of Riemannian model spaces. Riemannian model spaces. So, round S2, flat R2, and hyperbolic space. Now, in dimension 3, something weaker, but still absurdly strong is true. So this is known as geometrization of 3 manifolds. Geometrization of, well, closed 3 manifolds. And what it says very roughly is that every closed 3 manifold M can be decomposed into elementary pieces. Elementary pieces. Okay, next slide. Which are quotients of model spaces. Model spaces. In particular, the 3-dimensional Poincare conjecture has been resolved using Ricci flows, so techniques from geometric analysis. So the 3D Poincare conjecture was resolved using tools from Riemannian geometry. So basically, the quite possibly most central question we had in three-dimensional manifold topology was resolved using methods from Riemannian geometry, which of course made a lot of people very unhappy because there's still no topological proof of this fact. The fact that, you know, every simply connected closed three-manifold is already S3. That's quite unfortunate, but it tells you how powerful Riemannian geometry is in low-dimensional topology. Riemannian geometry. This is, yeah, quite surprising somehow. And it stops being true in dimension 4. In dimension 4, topology becomes sufficiently complicated so that it becomes very, very hard to make general conclusions about the topology of four manifolds using Riemannian geometry. But in dimension 3, somehow you can still do it. It's truly remarkable. And there's other reasons to think why, you know, to somehow suspect that Riemannian geometry might help you in understanding contact topology, but I'm not going to go into too much detail here since I'm already fairly late. Let me instead tell you how one might actually try to, so, you know, section 2.2, how to use Riemannian geometry. Okay, so how do we, you know, given a contact manifold, how do we pick a Riemannian metric and apply it in such a way that it tells us something about the underlying contact structure? Again, I'm gonna have to start with a definition. A pair alpha G, where alpha is a contact form and G is a Riemannian metric, is called compatible. Compatible if, okay, first, the norm of the Riemann vector field is supposed to be 1. So remember, given alpha a contact form, we can associate with a unique vector field that you can sort of think of as its dual in the space of vector fields. So this is supposed to have norm 1. Secondly, our alpha, the Riemann vector field, is supposed to be orthogonal to the kernel of alpha with respect to the metric G. I'm going to draw a picture in a second. And thirdly, remember that alpha wedge d alpha gives us a volume form, and similarly, a Riemannian metric induces a volume form on the manifold it's defined on. And these two are supposed to play well with one another. So there's a proportionality factor, which I call lambda, or G, and we want lambda to be constant. All right. Yeah, so I promised a picture. Here's the picture. So in every tangent space in the manifold M, we have some plane defined by alpha. So that's exactly the kernel of alpha. And then in the same tangent space, we also have R alpha. We want this to be orthogonal to the plane field. A different way of saying this is that the metric G should split as a metric on the plane field psi plus the tensor alpha. And this direct sum is taken in such a way that our alpha is orthogonal to the plane field psi. So this is my notion of compatibility, or actually not mine. This goes back, I believe, to Richard Hamilton and actually Chern. They tried to understand some of the properties of such metrics. And one of their conjectures from back then was like solved last year. That was quite exciting, actually. But I'm not going to go into that. Instead, I'm going to point out two obvious problems with this approach. So there's like two problems that, you know, immediately jump at you here. So two problems. First, alpha is a contact form, not structure. So remember that in contact topology, we're not really interested in the contact form, but rather in its kernel, the plane field distribution. However, we have used the one form alpha in the definition of a compatible metric and contact form. So somehow this is something to keep in mind. There is a lot of multiplicity going on here. For example, if you take a positive function f and you multiply alpha by this positive function, then f times alpha has the same kernel as alpha. So they describe the same contact structure, but as contact forms, they're quite different. In particular, the induced ray vector field is very different, and so also somehow compatible metrics look very different. Because remember, it's the ray vector field that is being used in order to define compatibility. And secondly, even with alpha fixed, we had so the metric has the form G on the plane field plus alpha tensor alpha. There's still a lot of freedom here. You can still choose you know, basically any metric on the plane field, and it's still going to give you a compatible metric. That's still an infinite dimensional space that you can choose from, and people are generally struggling to find somehow a good choice of compatible metrics. So whenever you have a contact form, it's very easy to construct a compatible metric, but unfortunately, it's just too easy. The space is huge, and this is, I think, one of the main reasons why people have been struggling to really prove good results in this intersection. But you know, there's these two obvious problems. Why do people still try to prove something here? Why, you know, how do you do anything with this setup, basically? Well, I would claim that there is one very strong result, so an Inventionis paper by Etnaya, Komendacic, and Marceau, which really justifies this attempt at proving something here. So it's the following theorem. So this is due to Etnaya, Komendacic, and Marceau. So I'm going to just, you know, summarize basically a couple of their results. So first of all, okay, so given a three-manifold and a compatible pair of a contact form and Riemannian metric, so alpha G compatible, we have the following. So first, R alpha, the ray vector field, is geodesic. Secondly, how should I put this? Secondly, the geodesic balls centered at points and the geodesic spheres centered at certain points are well understood from a contact topological point of view. So let me perhaps put it like this. And now we have alpha restricted to, you know, the ball of radius r. are well understood from a contact topological point of view, you can just, basically write down what's happening there. So if you take a geodesic ball with respect to a compatible metric, you really understand a neighborhood whose size you can quantify very well from a contact topological point of view. And thirdly, yeah, I guess that's somehow that's maybe the more precise version of what I was saying just now. There are quantitative bounds on the size of, let me call it, Darboux neighborhoods. So remember the Darboux theorem told us that every point has a neighborhood that looks standard. But if you go beyond just, some neighborhood, suddenly the contact topology in that neighborhood may no longer look like the local model. It's really just that we are guaranteed the existence of some neighborhood that looks standard. We don't necessarily know that it's big. And in this framework, these three managed to prove that actually there's bounds you can compute, which tell you that as long as you are looking at a geodesic ball that is whose radius is less than that bound, you are still in the Darboux case. You are still in the Darboux neighborhood. And then they managed to prove the theorem that actually gets them into invenciones. And that's the so-called contact sphere theorem. Contact sphere theorem. Yeah, okay, let me put this on a new page perhaps. So I have a bit more space. So yeah, so let's put this here. Contact sphere theorem. And what they prove here is that if M3 alpha G, so that's alpha G compatible. And G satisfies some sectional curvature pinching. Let me know if you're not familiar with those terms. So basically it means that, okay, let me first state the result. Then the universal covering of M3 with the universal covering of the contact form. Well, actually, I'm just talking about the structure here, but I want it to be co-oriented. Is contactomorphic to S3 with its so-called standard contact form, or let me say slightly different, to some alpha where alpha is tight. So they've managed to find some curvature condition on a compatible metric, which really tells you something about the topology of the underlying plane field, something that's absolutely non-trivial, something that's not just information about, say, the Euler class or some algebraic topological invariant of the plane field, but actually some contact topological quantity. The sectional curvature condition here just tells you that, first of all, you want the sectional curvature to be positive, quite positive, in fact. So if you know some Riemannian geometry, then this already tells you quite a bit. This already tells you that the fundamental group has to be very simple, for example, and it's not too hard to conclude that in fact you're looking at the sphere here. That's Klingenberg's famous sphere theorem. But what they're saying is that if such a metric is compatible with a context form, then you can even say something much stronger, not just something about the topology of the underlying space, but about the topology of the underlying plane field. And yeah, so that's a really remarkable result, and I think this is what much of the hope of somehow this entire approach hinges on. I meant to give you a sketch of the proof, just some idea, but I think I'm sort of running out of time. So instead, perhaps I can tell you why I think that even somehow disregarding this result I just told you about, this approach to context topology is very interesting. And somehow the picture goes like this. So you have, we are in the study of three-dimensional closed manifolds. Not necessarily closed actually, but in most what I'm discussing, it's closed. And we're looking at the intersection of geometry and topology and analysis. And on both sides of this divide, there's a couple of fields that like to interact with one another. So personally, I have contributed to this side, so to topological fluid dynamics. So this is here on my picture. Here in the bubble in between, let's say we have contact topology and Riemannian geometry. This connection to topological fluid dynamics essentially works in this way. So if you have a contact form, then that is compatible with the Riemannian metric G, then alpha satisfies the equation curl G, alpha is equal to lambda alpha, where curl is really the curl you know from vector calculus, only on one forms. So you can somehow dualize this operator and have it act on one forms instead of vector fields. And so these compatible compatible contact forms, they satisfy this equation. And it turns out that this is a really well-studied equation. It's called the Beltrami equation in fluid dynamics, and it describes sort of chaotic steady-state solutions to Euler's equations from fluid dynamics. And so using this connection, people have constructed really exotic solutions of Euler's equations. They have constructed solutions. So for example, this year, together with Daniel Peralta and Alberto Enciso, we constructed solutions that are isolated as solutions of stationary Eulers in the space of one forms with respect to the C1 topology. And this was somehow an open question. People didn't know how to construct such solutions. But using the flexibility you get from contact topology, you can actually do it. It's just that people didn't know how to do such a thing. And so this is like one interesting connection you have. Then the other thing that I've been working on is the connection to spectral theory of the curl operator. So if you look at this equation I wrote down, earlier, so curl alpha is equal to lambda alpha, then you see that this is an eigenvalue problem. And indeed, these sorts of eigenvalue problems can be studied from a contact topological point of view. Introducing this takes some time, which is why I didn't choose to present that for this particular talk. And also because I think it's not really analysts in the audience, so maybe that wouldn't have been that interesting. And so, and conversely, spectral theory of curl has a way of impacting the information of the underlying somehow plane field. And this is something that I plan to explore. And on the more geometric and topological side, contact topology interacts with symplectic topology and the theory of J holomorphic curves. And and then with somehow more dynamical questions. So I'm just gonna write here honors of flows, but there's been some breakthroughs in the last 2 years. And all of these things talk to one another, which I find quite exciting. So for example, people have used tools from symplectic topology to say something about results in fluid dynamics. And there should be a way, I think I know how to do that, how to use invariance from symplectic topology to say something about the spectral theory of curl, and potentially also the other way. That would be very cool. And similarly, okay, so let me maybe close by saying that at this intersection of contact topology and Riemannian geometry, there's a couple of interesting results, but people haven't really found an extremely, let's say, compelling way of building a general theory. At the same time, the people that started working on this problem all found pretty interesting, somehow, other ways of connecting contact topology with the study of other objects. So, for example, students of John Etnayer, they were told for their PhD to study this intersection of contact topology and Riemannian geometry, but then they ended up going in the direction of dynamical systems and honors of flows, which really interacts well with this study. And they have contributed to a really cool breakthrough result last year. I myself also, was similarly told to do something at this intersection. But then I ended up going into spectral theory of the curl operator, and it was extremely helpful to know about this intersection of contact topology and Riemannian geometry. So at the present stage of development of theory for these particular questions, I would say that it's been extremely productive to think about these problems, even though for a general theory of the interaction of contact topology and Riemannian geometry, people haven't made that much progress. I think it's one of those things that is somehow at the intersection of very well-known fields, and there's a lot to be done there still. But not that many people are working there yet. So this is somehow a piece of advertisement. So if you have grad students or no grad students that are looking for projects and you have some expertise in one of those things, there's a lot to be done here, and I have a lot of somehow ideas for projects that people could do. And I think it would be a good idea for some grad students to start working on something here, because there's just still a lot to be done here. Not that much, theory to be lost in yet. Yes, so I think this is where I'm going to stop. This was 1 hour.
Thank you for the great talk. Are there any questions, remarks?
So you say about the contact sphere theorem, who proved it and how?
Okay, so the contact sphere theorem was proven by the people I've mentioned previously. So that's John Etnayer, Rafal Komandarczyk.
I see. Yeah.
Yeah, and Patrick Masson. And
So
the way
each year?
that was 2012.
Already more than 10 years, yes.
Yes, more than 10 years. There have been improvements to this result, but the fundamental result was 12 years ago. And the somehow primary method is using somehow this curvature condition tells you that your space necessarily decomposes into two geodesic balls, and they really understand well how they glue together using the compatibility condition. And then somehow ideas from algebraic from symplectic topology tell you that this gluing is well behaved from a contact topological point of view, and you don't get any over twisted disks, and so the resulting plane field contact structure is tight. That's somehow the very rough idea.
Yes, so the idea is that to put extra Riemannian geometry as extra data, then it can you more find each kind of contact meaningful. That's nice, yeah. So each problem can be, you only say something of the topological fluid dynamic, and each condition that for you that's the most interesting that can be done using this.
Okay, let me give you one problem that one could tackle here. So for topological fluid dynamics, suppose you have a torus in three-dimensional space, and I'm really thinking about the solid torus here. And you want to solve this problem. So that's the Karl operator. You look at this eigenvalue problem on the torus. So this is solutions of this eigenvalue problem turn out to be energy minimal magnetic fields for the ideal magneto-hydrodynamics equation. So this is an object that people actually do simulations for because they're interested in magnetic fields that satisfy this equation. And now it would be interesting to know whether you can prove anything about the dynamics of this vector field. So say you can solve this eigenvalue problem on the torus. But of course, you don't know exactly what the solution looks like. So it would be cool to be able to prove something about the behavior of this vector field. And so how do you do it? One idea would be to take this vector field defined on this solid torus, and now you compactify. Actually, the torus is compactified. It is compact, but let me not say compactify, but glue another piece to the solid torus. So that's S1 cross D2 to S1 cross D2, so that you end up with a closed manifold that has a vector field V tilde that has vector field V tilde coming from V and satisfies similarly V tilde is equal to also satisfies this eigenvalue problem. And now it turns out that this means that the dual of alpha with respect to a certain metric, let's call this alpha, is a contact form. And to this, you can associate invariants from symplectic topology, which contain dynamical information. And if you do this entire process in a very smart way, you might be able to use this dynamical information to go all the way back and say something about this initial vector field. So that somehow very roughly is an idea for how one could do something like this.
Just a basic question about this particular problem that you described. So somehow your alpha, right? So if you consider it on the original solid torus, will it make it convex at the boundary, or like how you do precisely? Like, or you do it just topologically and you don't really care like how alpha could behave, or like what?
Okay, so the important thing for someone who's actually interested in fluid or magnetodynamics on the torus would be that the vector field is tangent to the boundary of this solid torus. But you know, from convexity as a contact topological concept doesn't really play into this. You know, no one in that field would care what the contact topological properties of the boundary are. So I'm trying to not make any assumptions about this. And you don't need to. I think there's a way of basically extending the context structure here to a larger space so that you still retain in this process some dynamical information. So that would be one thing that people could work on.
I agree with you, but I mean, convexity is quite often important for gluing, because basically like it's much easier to glue along the convex.
I agree.
Problem.
I agree, but on the other hand, I actually understand quite well what's going on at the boundary without assuming convexity in this particular setting. Of course, I can't yet, promise that this is enough for what I want to do, but I think I understand the context structure on the boundary sufficiently well, even without assuming convexity.
Can I also ask you about the diagram that you've drawn? Can you get to the diagram with Sanos flows and other stuff?
Oh, this one?
Yeah, the last one.
Yeah.
So you mentioned that you actually see connection between like all parts, like at the top and at the bottom, and how and also flows are related to spectral theory of curl. Like, is there like a clear connection there?
Okay, so actually, sort of, yes. So this was one paper that I was briefly mentioning when I was talking about this. So actually, I was talking about this connection here, but it's sort of related to spectral theory. So what we did in order to what people want to do is they want to construct exotic solutions to the Speltrami equation, because it gives you a rich example class of stationary solutions of Euler's equations that people couldn't construct otherwise, that have somehow some exotic behavior, and this makes you understand solutions to Euler's equations better, because you know somehow what kinds of things can happen. And in our particular case, we used a rate vector field that is also Anasov, like for example, the geodesic flow on a curve on a surface of negative sectional curvature. And then we use dynamical properties of this Anasov flow to tell us something about the structure of any nearby stationary solution of Euler's equations. And then combining this with some insight from spectral geometry of the curl operator, we managed to conclude that actually this solution is isolated in C1 in this space of solutions to stationary Eulers. So that's of course just the one direction. We used somehow dynamical information from the theory of Anasov flows to say something about stationary solutions of Euler's equations. The other direction, it's not so clear to me. So hopefully I'm soon gonna talk to Mamo Soni about this, who recently had this breakthrough in the theory of Anasov flows. Hopefully there's something there as well that would be cool. And I think it's not completely unrealistic.
I see. Thank you. Are there any other questions, comments, remarks? If there are none, then I believe we can close the session. And thanks a lot, Willi, once again for giving this great talk. So if you could share the slides, I would really appreciate it. So it would be nice to have them on our webpage. And yeah, it would be nice to see you at some point, like physically in Prague. So
I would be happy to, yeah.
Sure. Yeah, sorry, this time is just online, but